Welcome to this video series on frequently asked questions about the Java language. In this ongoing series of videos, we'll answer commonly asked questions about the Java language. You'll come away from this video with a solution to a question that you as a developer may have. In fact, these questions have been asked by thousands of developers, so you're not alone. Our approach to every question is simple. First, we pose the question about the Java language, Java development, or best practices. Then we fill in any background material so the question makes sense. Next, we'll get into the details of the question and discuss it further. Then we'll come up with an answer. As a bonus, we'll go deeper on the answer and look at a code example to show you what to do and in some cases what not to do with a counterexample. Stick around until the end of every video where we'll discuss the solution from an application security point of view. We'll let you know what to look out for to ensure your code stays secure. For more videos like this, like and subscribe to be among the first to know when we release something new. Ready to get started? Let's go. The question we address in this video is how can we create an executable jar bundled with the dependencies using the Maven build tool. So let's say we've created a project and we want to distribute it in a single jar file. Let's say that we're using the Maven build tool to compile and package our application. How can we package the jar so it includes all the dependencies in a single jar file, sometimes referred to as a fat jar? And finally, let's make the result a self-running jar. Okay, that's a lot to cover, so let's get started. First, we'll begin with a little background on the Maven tool. Maven is a free open-source build automation tool available from Apache, originally released in 2004. It prescribes a simple, uniform way to construct projects and provides a tool for easy build automation and packaging of applications. It also provides dependency management and will retrieve direct and transitive dependencies necessary to successfully build an application. The functionality of the tool can be extended through the use of plugins, including custom plugins that you write yourself. The tool has a library of archetypes that define common project templates. Using these templates makes it easy to quickly and consistently set up a project and organize all the resources in a way that makes logical sense to developers and tools alike. Project configuration is stored in a file called pom.xml. Let's look at how we can use the Maven tool to generate a starter project using an archetype. From the command line, we'll invoke the Maven tool. It's abbreviated as MVN. We'll specify the archetype for the project that we want to create, along with the properties that we'll use to create the project. We'll specify each property with the -d flag. The archetype plugin is like a templating toolkit. The goal we invoke is generate. We'll discuss plugins and goals a bit more when we get into the coding section. On our command line, we specify the archetype ID to be generated. In this case, we invoke the Maven-archetype-quickstart archetype. This will create the project structure, including directories, some sample code, and a POM file for a simple Maven project. There are many other archetypes, including ones to create websites, web apps, Java Enterprise Edition applications, and many others, including custom archetypes for specific tech stacks. We'll also specify the details of the application we plan to construct. This information includes the group ID, artifact ID, and version, often abbreviated as GAV or GAV. The group ID uniquely identifies a project across all other projects. This will often be the same as the package structure of your application. In our case, we're using the package name of com.beginsecure.app. The artifact ID is the name of the jar to be created without a version. In our case, we'll be using the name sample-app. And finally, the version is any number we wish to use to indicate the release of the project. In our example, we're not specifying the version used to create the GAV, so we use the default value provided by the plugin. In our example, the version we do specify is actually the version of the archetype we'll be using in our creation process. In this case, version 1.4 of the archetype. Our final parameter is interactive mode, which we set to false. This means that we'll supply all the information on the command line invocation of Maven and don't wish to be prompted for any input. The best way to look at a Maven example is on the command line. So let's jump into the coding section now and get some hands-on with the Maven command. For this lesson, we'll be working in Ubuntu Linux. First, let's run ls to see that there's nothing in the current directory. Let's take a look at a few overlooked features of Maven. Let's run maven help:help. In this case, help is a plugin. That's the help on the left side of the colon. So what is a plugin? Maven is just a framework for a collection of plugins. Plugins are used to do the actual work of creating jars, compiling code, running unit tests, etc. Plugin behavior can be modified through a set of parameters exposed by a descriptor for each plugin goal. So what's a goal? A goal is a specific task that contributes to the building and managing of projects. When we invoke plugins, we specify a goal to perform. In this case, the goal is also called help. It's the help on the right side of the colon. Scrolling through the output, we see that help has 8 goals, including active profiles, all profiles, describe, effective pom, effective settings, evaluate, help, which we've already seen, and system. Let's run the goal describe from the help plugin and specify that we want to describe the compiler plugin. This will print out details on the goals available in the compiler plugin, which include compile, help, and test compile. And if we take it one step further, we can specify that we also want to see detailed help on each of these goals. Running this command gives us detailed information about the parameters available for each goal, along with the description as well as the default values. This information can be invaluable when trying to figure out a Maven-related problem. Okay, enough fun stuff. Let's get down to business. Let's enter the same command line that we saw earlier in our slide presentation. We'll enter Maven, again abbreviated as MVN. We'll invoke the generated goal of the archetype plugin. We'll specify the parameters we wish to supply. The group ID will be com.beginsecure.app. The artifact ID will be sample-app. The archetype version will be 1.4. And the archetype artifact ID we'll generate will be maven-archetype-quickstart, which is just a simple project outline, along with some starter code and a pom.xml file. And finally, we'll specify false for interactive mode. When we run the command, we get a lot of output. At the end, we see the most important thing, which is build success. We also see echoed back to us the value of the parameters that we either supplied or the values that were set for the ones that we didn't override. Notice that for our gav, the version will be set to the default value of 1.0-snapshot. So our complete gav will be com.beginsecure.app sample-app 1.0-snapshot. This will be more clear when we start editing the POM file. Okay, let's type in ls to see what we did. We see there's a directory called sample-app, which is the artifact ID of our project. So let's cd into that directory and run ls again. We see that we have a pom.xml file along with the directory called src, or source. Let's run the tree command to see the entire directory structure. We see some files were created along with a lot of directories. Under src, we see 2 directories called main and test. Then the rest of the path is the same: java/com/beginsecure/app. Then there's a file called app.java and a file called apptest.java. App.java is our main application code that was generated for us. And apptest.java is the outline of a test app, including JUnit, which can be used to create and run test cases for our application. We'll explore JUnit in a future video, but for today, let's look at the source code in app.java. We'll use vi to open the file, and we'll see that it's just a simple Hello World application. For now, let's quit the vi session, and back in the sample app directory, let's run maven validate. This command will check our pom.xml file to see if it has any errors. Since we just generated the file, there are none, and we get build success. Now let's edit the pom file and take a look at some settings. First, we notice the values of the gav, both the specified and default values used when we generated this project. Now let's search for the string 1.7. We see that the default compiler for source and target are both Java 7. Let's change them both to version 8 and save the change. Now let's run Maven validate again to make sure our changes were good. Once again, we see build success, so we know everything is fine. Now let's run Maven package. Package is not a goal, but a phase. A phase is a step in the build lifecycle, which is an ordered sequence of steps. When a phase, like package, is specified, every phase in the sequence up to and including the one specified is run. The phase steps for package are validate, which we saw already, compile, which compiles the source code of the project, test, which runs the compiled source code using the JUnit test framework, and then package, which takes the compiled code and packages it into a distributable format, for example, a jar file. If we run the tree command now, we see a lot of output related to the test results, but the thing we're interested in is the file in red called sample-app-1.0-snapshot.jar. The file is located in the target directory. Let's run ls on the target directory, and let's run the code we just packaged and see what happens. If we run java-cp and specify the class path will be the target of the jar that we created, followed by the fully qualified name of the app application that we looked at, including the package and class name where main exists. Then we get the output, which is the hello world message. Okay, step number 1 is complete. We created a simple project and packaged the application into a jar file, and we were able to run it, although it wasn't a self-running jar. For the next step, let's specify a new plugin, the Maven assembly plugin, and we'll use one of the prefabricated descriptors, jar with dependencies. And for the main class, we specify the fully qualified class with the main method that was generated for us by the archetype when we created our Maven project. In our case, that will be com.beginsecure.app.App. And let's save that change. And run the validate phase again to check to see if our pom is still good. We see build success, so we're good. Now let's edit the app class and make it a bit more interesting. We want to get rid of the printline statement and add some code that will require a dependency. In this case, we'll add some code to parse a JSON string. This will require the addition of a third-party library to do the work. Let's add a string object, sample.json, and set it equal to an empty string first, and then let's add in the content to build a JSON object literal. First, we'll put in a set of empty braces to create our JSON object literal. Then we'll put in 2 key value pairs. First, we'll have a key called ID and set it equal to 1. Then we'll have a key called name and set it equal to Mary. We'll escape the quotes with backslashes and add in the colons and commas as needed to create a valid object literal. Next, we'll need to create an object representation of the string we just created. To do this, we'll create an object variable called job of type JSON object. We'll pass in the string we created to the constructor, so job will be a reference to the JSON object representation of our string. And finally, let's print out the value that corresponds to the key name, in this case Mary, using a system.out.println statement. To do that, we'll invoke the getString method of the job object and pass in the key name. Finally, let's add our import statement to the code to include org.json.json object. So you may be asking, what's the point of all this? What we want to do is simply write some code that will require the use of an external third-party library. This will force us to include it in the POM file, so the dependencies included in our build will become part of the executable jar that we'll create. So let's save that code and change directories back to the sample app directory where the pom.xml file is located. Here, let's run Maven package. When we do so, we get errors. This is because we have not included the necessary dependencies to resolve JSON object. So we'll need to add the org.json jar file to our project using the appropriate gav. Let's bring up a browser and go to Maven Central to find the proper gav. Here we can enter search criteria for the package. If we enter g:, and then org.json, we'll search for the artifact with the group ID of org.json. We see that there are two choices. Let's hit enter, and we see the first one, which is the one we're after because it's more current, has more versions, and the artifact of JSON, which is the one we're after. So let's select the first one. Here we see a page that lists some of the details of the project, along with the formats for inclusion in different build tools, such as Maven, Gradle, and others. We're using Maven, so we'll go ahead and select the first entry for Maven and copy that entry. Then back in our project, we'll edit the pom.xml file, and then go down toward the bottom where the dependencies are listed. Let's open a new line and copy in the new dependency entry. And save that code. Then back on the command line, we'll enter the Maven command, maven clean compile assembly : single. Clean will get rid of all previously compiled Java class files and resources from any prior builds. Compile will compile the source code of the project. The assembly plugin will allow us to combine the project output into a single distributable archive that also contains the dependencies. When we run the command, we see that we get build success. Also notice that we built a jar file in the target directory called sample app 1.0 snapshot jar with dependencies. Now let's run that code. To do so, we simply enter java-jar and specify the jar in the target directory. When we run the code, notice that we don't need to specify a main class file, since that was provided by us in the POM file and ended up in the manifest file of the jar. When we run the code, we get the output from the main method in the app class that we wrote. We see that the key name contains the value Mary in our JSON string. If we cd into the target directory and run ls, we see our jar file. Let's copy that jar to /temp, and then go to that directory and run the same jar file from there. When we do, we get the same result, indicating that our jar is completely independent of the location where it's run and is a standalone executable jar with all dependencies. So, are there any security concerns around building jar files? As with any application, we always want to pay attention to the third-party libraries our applications rely on. We want to understand what packages are used by our applications and be aware of the security vulnerabilities in those packages, as well as in the packages used as indirect or transitive dependencies. We want to know how well maintained these components are, how frequently they're updated, when they were last updated, and if the maintainers of the project are quick about resolving known security issues. You should also make sure you're using a reliable repository as the source of all your components, and that you specify the gav correctly to ensure you get the artifact, group, and version that you actually expect. Of course, it's up to you as a developer to keep your code current by updating your application build to include new releases of third-party components as they're released. Failure to do so will cause the accumulation of technical debt that will be hard to overcome in a moment of crisis when a component is found to have significant vulnerabilities that require immediate remediation. Supply chain security and the reliance on third-party code is a significant concern for any commercial application, and one that should have proper controls and oversight built into the process. Thanks for watching. We hope you enjoyed this video. Please like, subscribe, and share this video with others. Right now, while it's still available, go to www.beginsecure.app.App.App to get our free ebook on how to write more secure Java code. When writing code, remember to always begin secure.